Right. Let's go number 2 and 3. Which form of electromagnetic radiation has the longest wavelength? Now you can just memorize the spectral chart, or the way I look at it is longest wavelength implies the lowest energy. So then I look at the choices and say, which one's the lowest energy? Well, gamma rays the very highest energy possible. You know, X-rays are next. Infrared is next. Microwave is next. And radio waves are the longest wavelength, the lowest energy. So radio would satisfy the number 2, which is C. Number 3. Which of the following frequencies corresponds to light with the longest wavelength? Remember these, the association of wavelength and frequency is this relationship here. So that's frequency, that's wavelength, they're inversely proportional. So the longest wavelength, the biggest value here will give you the smallest value there. So the smallest frequency, smallest number for frequency would satisfy that condition. Longest wavelength means the smallest frequency. And I look at since these are all in scientific notation, I look at the powers of 10 first and find the smallest power of 10 if that's at all possible. And we've got 13, 5, 20, 12, and 9. 5, 10 to the 5th would be the smallest out of all those groups. And we've only got 1 10 to the 5th, so that's your answer. If we had a pair like 10 to the 5th, then we look at the coefficient to see which one of those is small. But since 10 to the 5th is all by itself, then B would answer that question.
And you said the longest wavelength is the lowest frequency.
Correct. Right, because speed of light is a constant. And if you have 2 variables in the product, a product of 2 variables equal a constant, they're always inversely proportional. Just like Boyle's law. All right, number 6. A line in the spectrum of atomic mercury has a wavelength of 254 nanometers. 254 nanometers, all right. When mercury emits a photon of light at this wavelength, the frequency of this light is. Okay, if all we're going to do is convert that to frequency, then we're back to this relationship. Right, we want to find that value right there. Frequency is speed of light divided by wavelength. But these have to be in fundamental units. Right, speed of light is 2.9979 times 10 to the 8th meters per second. And wavelength needs to be in meters. So the way I convert this to meters is I say, what is nano equal to? Nanos equal 10 to the minus 9th meters. So, and your calculator will accept this input. It doesn't have to be in scientific notation. It can be exponential. 254 times 10 to the minus 9th meters. All right. So I say 2.9979 exponent 8, and then divide by 254 exponent. It's not. And I get, let's see, 3 significant figures. 1.18 times 10 to the 15th reciprocal seconds. Oops. I put it in wrong. Sorry. Let's try that again. 2.97. Hold on a second.
That was right. You had it right.
Did I have it right?
You did.
Oh, okay. Yeah, because the sign changes when it goes up there. I thought the calculator was wrong. 1.18 times 10 to the 15th reciprocal seconds. Or if all the answers were in hertz, you just substitute that because that's what it means. Hertz is another unit that means exactly the same thing as reciprocal seconds.
And that 2.,
99, that's a 9, sorry. 2.9979 times 10 to the 8th
speed of light.
is the speed of light, yep. Okay. Let's check out number 8.
Is that on the useful information or no?
Yes,
Okay.
should be. Somewhere. Find it. Let's see. There it is.
Yeah, they were
Left-hand column in bold. Down the left-hand
underneath
side.
1 atom equals 1 bar.
1 atmosphere equals 1 bar.
That's what I meant.
Okay, number 8. Green light can have a wavelength of 543 nanometers. And we're given that the energy of a photon of light, is, okay, we're looking for energy. That means we've got Planck's constant times frequency. Or Planck's constant times speed of light divided by wavelength. Right? Because what? Because C equals wavelength times frequency. So if we solve for frequency, that puts C divided by lambda. This needs to be in meters, so we're going to convert that to 10 to the minus 9th again. 543 times 10 to the minus 9 meters. And Planck's constant is in your useful information. I have to look that one up.
That's
6.6 something, yes.
Times 10 to the negative.
6.626 times 10 to the negative 34.
6.626 times 10 to the minus 34.
Yep.
Yeah. And then speed of light. 10 to the 8th meters per second. And then wavelength in meters. Go. Six exponent 2.9979 times 543 exponent change the sign about. So I get 3.66 times 10 to the minus 19th joules, which is C. Okay. Right. 8. And number 11. Let's see. How many of the following are correct? Okay. 1, 2, 3, and 4. The first one, the importance of the equation equals mc squared is that energy has mass. Is that reasonable? Yeah. It's actually the equivalence of energy and mass. And that's another way of saying it. So this one's true. The electromagnetic radiation can be thought of as a stream of particles called photons. Yep, that's true also. That's the particle nature of light. 3, electromagnetic radiation exhibits wave properties. Yep, that's true also. Right, light's both wave and particle. And 4, energy can only occur in discrete units called quanta. Yep, so they're all true. 4. Okay, we're going to be basing 12, 13, and 14 and 15 are going to be based upon that table. Right? So 12, 13, 14, and 15 are all based upon that one table. What does 12 say? Electrons have wave properties. The table is giving you properties that are associated with the question. Does which one of those properties explains the question? Electrons have wave properties. Electrons behave as waves. So which one of those is evidence of wave properties of electrons? The emission spectrum of hydrogen? I don't think so. Photoelectric effect? That's particle properties. Scattering of alpha particles by metal foil? Diffraction. What is diffraction? Remember, if you have a wave coming along here and it strikes that barrier, then this serves as a point source. Right? Diffraction. Electrons behave as waves, and probably would have been, well, cathode rays are particles. The best example of electrons as waves is the electron microscope. It uses the wave property of electrons to investigate very, very, very small things. And it uses that because it takes advantage of the diffraction of electrons in the microscope. How about electromagnetic radiation has wave characteristics? Well, that's diffraction again. All of those, A through E, all those except one, demonstrates particle nature. Yes. So this one is D, this one is D. Right, electromagnetic radiation has wave characteristics. That's demonstrated by diffraction. Electrons and atoms have quantized energies. Okay, quantized energies references emission spectra. Quantized energies means if you have a nucleus and you have these various levels of energy, then the electrons can only move between those levels in discrete amounts. That's what quantum means, discrete amounts only. So it can move either way. It can move that way or that way. And that emission spectrum of hydrogen is actually electrons moving from higher to lower. Because if they move from higher to lower, that means higher energy to lower energy. Energy has to be conserved. So when they move from the higher to the lower, they give off energy. Okay, that's the emission spectrum of hydrogen. Demonstrates 14. Quantized energies of electrons in atoms. That's And 15. Spacing between atoms in a crystal is on the same order as the de Broglie wavelength of accelerated electrons. The de Broglie wavelength we haven't used the de Broglie equation yet. But the de Broglie wavelength simply states that all matter has wave characteristics. E equals mc squared says all matter is also expressed as energy. But de Broglie says that all matter actually has wave characteristics. I have a wave number that's associated with me. But I'm so big, the wavelength is huge. If it's small, the wavelength gets shorter and shorter and shorter and shorter. So diffraction is the only expression of waves in that list. So diffraction is a demonstration of the de Broglie wavelength of all matter. Okay, let's go to 16. I'm thinking if we want to calculate my wavelength, we'd have to convert my mass into energy and then use Planck's equation to convert energy into wavelength. And that would be my wavelength. And we could combine those two equations so we'd only have to do one calculation. But I'm not going to do that unless we have to. The 4 lines observed in the visible emission spectrum of hydrogen tell us that what? The hydrogen molecules that came from have the formula H4. That's kind of silly, actually. How many are there? 5. Right, this one's false. There's no such thing as H4. We could observe more lines if we had a stronger prism. That's been tried. Right, shine hydrogen emission given off a combination of wavelengths. Right, you send it through a prism and it gives you these 4 lines in the visible spectrum. We saw that demonstrated. Well, some scientists, and this is early on, back the beginning of the 20th century, they stuck another prism right here, right? And said, all right, what happens to that light? Single wavelength. So they stuck another one here, single wavelength. You can't split the wavelength any further. So we could observe more lines if we had a stronger prism? No, that's been tried. There's no such thing as a stronger prism. It either is a prism or it isn't. All right, so we've tried to split the lines further and we can't. So that line is unique for an electron transition from one level to the other. That means this one's also false. Stronger prism doesn't make any difference at all. How about C? There are 4 electrons in an excited hydrogen atom. No, there's only 1 electron in a hydrogen atom. How about D? Only certain energies are allowed for the electron in a hydrogen atom. That is definitely true. And E, the spectrum is continuous. No, it's not. I mean, the problem says line spectrum. So E was just, it's a filler. Just seeing if you're paying attention. $17. All right, for which of the following transitions does light emitted have the longest wavelength? Here we go again. The longest wavelength. The longest wavelength equals the smallest energy. And the smallest energy for an electron transfer in an atom is the shortest distance. Electron shortest transition. So what if we have 4 to 3, 4 to 2, 4 to 1, 3 to 2, 2 to 1. Let's say, so we're only going up to 4. So here we have 1, and we have 2, and 3 is a little bit closer. 4 is even closer still. That. So if we transition from 4 to 3, it's only going that distance. If we transition from 4 to 2 or 4 to 1, we're going a greater distance. Okay. And then if we go from 3 to 2, it's this distance. And if we're going from 2 to 1, it's this distance. The shortest distance in that whole transition sequence.
Hold on a second.
Yeah.
You said from 3 to 2.
Mm-hmm.
Why'd you go all the way to 1?
Oh, sorry. Yeah, you're right. My mistake. 3 to 2, and then 2 to 1. Okay. So,
And are those shells always like skinnier on the outside? You see?
yeah, they get closer and closer together as you get larger numbers. Yeah. So the shortest transition is between 4 and 3. That will give you the longest wavelength, the lowest energy. So A is the answer. All right, number 18. When a hydrogen electron makes a transition from n equals 3 to 1, which of the following statements is true? All right, we're going, electron is going from n equals 3 to n equals 1. Energy is emitted. Yeah. That's true. We're going from a higher energy level to a lower energy level. We're going to get Planck's energy out of that. Well, 1 and 2 can't be the same. Oh, wait a minute. Excuse me. Roman numeral 1 is true. Roman numeral 2 can't be true because you can't have both of them. You can't emit and absorb at the same time. The electron loses energy from a higher to a lower energy. Yes, it loses energy. And I bet 4 says it gains energy. Yeah, so that was false. And then 5, the electron cannot make this transition. That's false. So 1 and 3, which would be B, would be the correct answer to that.
If you're going from larger to smaller, it's given off.
Emitting energy, yes.
Okay.
Right. Because you have to conserve the energy. And if you're starting at a higher energy level and going to a lower one, energy's got to go somewhere. It's emitted. If you go from 1 to 3, then it has to absorb energy to get to a higher level.
Okay.
Let's see, 1821. Which of the following is incorrect? All right. So I don't see any squirrely ones in there like all are correct or 2 are not or that kind of stuff. So if A through E, they're all unique answers, we got to find out. We go down until we find an incorrect one, actually. All right, so A says that The emission spectrum of hydrogen contains a continuum of colors. That's incorrect. We found our answer. Right? A is wrong. It's incorrect. The rest of them should be correct. Diffraction produces both constructive and destructive interference. Yes, that's true. If you have a barrier, and this is referencing B, if you have a barrier with actually two slits in it, then when the wave strikes that barrier, you got this, you got 2 point sources, 2 new sources of wavefront. So they propagate out from here, propagate out from here. And the line I've drawn, think of that as a crest. That's the top. So wherever these crests meet, you get reinforcement, constructive interference. And wherever the line meets between 2 lines, that's a trough, that's destructive interference. And it produces no intensity at all. So if we have a detector over here, what you get is halfway between these, you'll get a very strong constructive interference of these 2. And then you get successively weaker. Out from here like that. And then you'll have these places in here will be the destructive interference. Okay. All right, so B is true. Let's see, we need to spend time on the others. C, all matter displays both particle and wave-like characteristics. Yes, I mentioned that earlier. D, Niels Bohr developed a quantum model for the hydrogen atom. Yep, it was a planetary system with those 1, 2, 3, 4, 5 energy levels. And the lowest possible energy state of a molecule or atom is called its ground state. That's a definition. The lowest possible energy state under conditions. And under these conditions, you're going to find that hydrogen, the electron will be in energy level 1. But if we increase, say, we find hydrogen in an atmosphere that has elevated temperature, there may be enough energy there so that the lowest possible energy that it can attain is the 2nd level or the 3rd level. That would be its ground state under those conditions. Okay, 22. Oh, I forgot to, let's see who, Michaela and Desiree. Oh. All right, 22. Which of the following statements best describes the Heisenberg uncertainty principle? Remember that one? Simply stated, for very small particles, like electrons or atoms, you can't know both where it is and how fast it's moving at the same time with any accuracy. You can know one of them, but if you know one of them accurately, the other one is unknowable, essentially. Right, and I put that formula up there, but I'm not going to bore you with that again. So, which one of these says that? The exact position of electron is always uncertain? No. Right, you can find the electron position, but you can't know how fast it's going, or you can't know its energy. The velocity of a particle can only be estimated. No, it's a comparison of the two, velocity and position. It's impossible to accurately know both the exact location and the momentum of a particle. That is true. That's in prose how we would say that formula. C is the answer. All right, 25. How many F orbitals have the value n equals 3? That's so we got n equals 3. Let's just review. Next one is L, right? Then M sub L and then M sub S are the 4 quantum numbers. So if we're looking at f orbitals, that's here where we give those numbers letter equivalents. So if you have 3, what are the possibilities for L? 0, 1, and 2, correct? Start with 0 and go up to n minus 1. So this is n minus 1 is 2. That's the maximum you can have at n equals 3. You can have that many subshells. This is the shell, subshell, orbital. All right, so what do we call these? We call that S, P, and D, right? So for n equals 3, you can't have any Fs. Fs are forbidden at energy level n equals 3. Principal quantum number n equals 3. You can't have S, so the answer is 0. Okay, how many F orbitals have n equals 6? Okay, so let's change it here. This would be 6. That means 0, 1, 2, 3, 4, and 5. So yeah, we can't have an F there. So how many orbitals does that mean? Well, now we're down to this level. If this is permitted, then how many can we have here? Minus 3, minus 2, minus 1, 0, plus 1, plus 2, plus 3. So that's 7, correct? Yeah, 7. 7 orbitals. This is the shell, subshell, and orbital. Those are common names for these quantum numbers. So you can have a maximum of 7 orbitals. That would be B. All right. If n equals 2, how many orbitals are possible? Now we're doing totals. So if n equals 2, n equals 2, we can only have 0 and 1. That's n minus 1. So how many orbitals can you have from this one? Right? That one gives us only 1, right? 0. This one gives us minus 1, 0, and plus 1. So you can have 1, 2, 3, 4. You have 4 orbitals for n equals 2. At 1 s and 3 p's. So that's why the answer is B, 4. That's the total number of orbitals you can have. We didn't focus on one of these or the other. It says total number of orbitals. That's why we added them up. Oh, I haven't been changing the numbers. That was 27, 28. Get back on track here, 28. All right, 28. A given set of p orbitals consists of how many orbitals? That's not right. A given set of p subshells, right? P subshells. So P would be, let's see, P would be 1. Subshell L equals 1. 0 is S, 1 is P. So we can have how many orbitals? Well, we can have minus 1, 0, plus 1. We can have 3. So that's why the answer is C. I need to change that. That's not worded correctly. A given set of, well, no, that's correct. A set of p orbitals. This is a set of p orbitals. That's p subshell, and these are the p orbitals. Yeah, okay, so it technically is correct. But the answer is 3. Minus 1, 0, plus 1. 29. All right, 29. Which of the following is an incorrect designation of an atomic orbital? All right, so A, B, C, D, E. What are our choices? We have 1s, 3d, 1p, 4f, than 6s. So what we're saying is, which one of these is not allowed? Is 1s allowed? Yeah, s is 0. This is 1. You can have only 0, n-1, right? So that one's okay. How about 3d? Let's see. 3n would be 0, 1, 2. S, P, D. Yep, you can have a 3D. Okay. Just, is it permitted? 1P, nope. We just said S is as high as it goes. It only goes 0, n-1. So that one's not allowed. And we found our answer actually. 4F, but you can have 0, 1, 2, 3, and this is F. So that's correct. And 6s, right? Any of the orbitals, any of the principal quantum numbers can have s orbitals. All of them can have s's. So the answer is C. 1p is not allowed. All right. Doing on time. Okay, we're good. (29:31). A point in the wave function where the amplitude is 0 defines what? This is definition. Right, if we have a wave function like that, this is drawn in 2 dimensions. Or if we had 3 dimensions, we would show density as the strength of the color. But if we look at it this way, and if we say, actually, that. So this is plus value, maximum plus, and this is maximum minus. Maximum plus, maximum minus. When it drops to 0, we're right here. That's a node. And if we look at our example, I think was s orbitals. So 1s would have an electron density that was uniform. A 2s would be bigger, but it would also have a region right here with no electron density. Right, so this would be 1s and this would be a 2s. And if for principal quantum number 2, you have 1 node. For quantum number 3, you have 2 nodes. Okay, so it'd be another way of looking at this. But if this is your 0 line, when it drops to 0, then you have a node. And that term node is not just unique to atomic physics. We speak of nodes for any time you have a wave function. So if we're studying sound, right, sound waves from a musical instrument, it'll produce pulses, and that's what you register as frequencies, right, pitches. But those pitches are made up of this sine curve, and it will drop to 0. That's another discussion. 32. How many electrons in an atom can have quantum numbers n equals 3 and L equals 2? N equals 3 and L equals 2. How many electrons? Okay, so now we're going to M sub L and M sub S. So if L is 2, how many M sub L's can we have? We have -2, -1, 0, +1, and +2. And then for each one of these, we can have a +½ or a -½ So 1, 2, 3, 4, 5. 2 times 5 is 10. You can have 10 electrons with n equals 3 and L equals 2. All right. One electron will have 3, 2, minus 2 plus 1/2, 3, 2, minus 2, minus 1/2. And you just go on across. So you can have 10 electrons in the same atom with these two quantum numbers. But when you pair up these, they have to all be different, right, according to the Pauli exclusion principle. So you can have a maximum of 10 elements. And that's why you have 10 elements here. Transition metals, you have 10 possibilities. Okay, 33. How many electrons can be described by the quantum numbers? N is 3. L is 3, right? And M sub L is 1. M sub L is 1. Well, from here, the only place you can go is down to here, either plus 1/2 or minus 1/2. So only 2 electrons. Oh, excuse me. No. Let's see if it's even allowed. If this is 3, you can have 0, 1, 2, up. 0. You can't have that. Right. That's why the answer is 0, because this is not allowed. You can't have L equals 3 for a quantum principal quantum number of 3. You can only have 1, 0, 1, and 2. That was a trick question. $34. Okay, what is the L quantum number for a 4s orbital? Oh, in L, 0, 1, 2. The L number is 0. Right? 0 is S. This is P, this is D. So it doesn't matter what that is. If L is S, it has to be 0 for the number. Zeros and S's go together. How about 37? Which of the following combinations of quantum numbers N, L, M sub L, M sub S do not represent permissible solutions of the Schrodinger equation for the electron in the hydrogen atom? In other words, which combination of quantum numbers is not allowed? All right. So we got, let's go across this way. N, L, M sub L, and M sub S. Got these possibilities. And E. All right, so for the first one is 9, 8 minus 4.5. 9, 8 minus 4.5. That'd be a plus 1/2. 8, 2, 2.5. 8, 2, 2.5. 6 minus 5. Minus 1.5. D is 6 minus 5. No, 6 plus 5 minus 5.5. And all are allowed. Okay. So I don't see anything wrong with the M sub S. They're all plus 1/2. So that's permissible. We can't eliminate any of them based upon that. If N equals 9, is 8 allowed? Yeah, N minus 1, right? So that's allowed, that's allowed. How about minus 4? Yeah, minus 8, minus 7, minus 6, minus 5, minus 4. That's allowed. So this one's allowed. Let's go back to the question. Not represent. All right, we're looking for the one that's wrong. Okay, 8 and 2. Yeah, right. 0, 1, 2. Right, so that's allowed. How about this one? It would be -2, -1, 0, +1, +2. Yeah, that one's allowed. So this one's okay. How about this one? 6 - 5. Can that number be negative? No, it has to be positive. Right, so we found one that's wrong. How about this one? Well, we found the wrong one. But let's see if this one is permitted. Yeah, n-1, that's true. And then -5, -4, -3. That one's okay. That one's okay. Okay. So this is our bad one, C. That was not permitted. All right, number 40. This is just a test of memory, I think. So what's the question? Who was the first chemist to recognize patterns in chemical properties of elements? Temptation is to say Mendeleev. He did recognize patterns, but he wasn't the first one. Lothar Meyer came along about the same time as, no, wait a minute. Yeah, that's right. Mendeleev and Meyer came up with periodic tables. We didn't even talk about Newlands. Bohr didn't care. Right? He was interested in physics, not chemistry. Dobereiner was the one who came up with the triads. He noticed similarities among groups of 3 elements each. So Dobereiner is actually the first one to recognize patterns. '41. Mendeleev is given the most credit for the concept of the periodic table of elements because he used the table to predict the existence and discovery of future elements and their properties. Right, so which one works for that? He emphasized its usefulness in predicting the existence and properties of unknown elements. Yep. That gets him the most credit for the periodic table is B. '44. The complete electron configuration of 10. All right. 10 with how many protons? 50. That means 50 electrons in the neutral atom. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p. Let's see. 10 is here. It's 1, 2, 3, 4. It's going to be down to 5p. So 4p6, and then we swing back around to 5s. 2, and then we go across 4d, and that's transitions, right? We're down to 5, period 5. That means these are 4d, 4ds, 5s, 4d, and then back up to 5p. And how many over are we in 5p? 1, 2. So this only has 2 electrons. Now let's count them up and be sure we're right. Okay, 2, 4, 6 is 10. 2, 4, 6 is another 10. Another 10. Another 10. And 8, 9, 10. So 10, 20, 30, 40, 50. That's it. That should be the one. Now let's see, how do we find that one out of this mishmash? Let's look at the end. 5p2. 5p2 is A, C, or D. Okay. Those are possibilities. I'm using test taking techniques here. And then back up. What's the next one? 4D10, right? A says 5D10, C says 5D10, and D says 4D10. Probably D. And then you can go in and check it, see if they're all in the right order, but it's pretty safe they are. So D is the answer. Okay. Think you can do that? Or you can either use that diagonal chart, which should be in here. No, here. Oh, there it is on the first page of useful information. There's your diagonal chart. And if you want to use the diagonal chart, you can just go diagonals and get these in the right energy order and then start filling in. All S's can only have two, right? It's just a zero. You can have up, down, spin, up, down, spin. P has 3 sublevels, right? D has 5, right? And with 2 electrons each. So that means this has 6, 2, 6, 2, 10, 6, 2, 10. And then what's left over? Or you can go to the periodic table and just go right down the line. The first two, hydrogen, helium, those are 1s. And lithium, beryllium are 2s, 2s2. And then we go over to boron through neon is 6 more. Then we swing back down to the third period, 2 more in the s orbitals, and 3 more. Aluminum through argon is 6. And you can just keep stepping your way down. Right? These are all p orbitals. Those are s orbitals. These are d's. Only when you get to the d's, if this is the 4th period, the d's are 3d. Step down 1. And that way you can fill in the chart without that diagonal. Just follow them one at a time. It takes a little practice, I'll admit. It's a newly acquired skill. It's not something that you could wake up with. Or you can't, like subliminally, like put your headphones in, start the player, go to sleep, wake up in the morning with just, I'm a genius. It doesn't work that way.
Good though. I wish it did.
Yeah. Or you can like that. You remember this old movie with Keanu Reeves called Johnny Mnemonic, right? He had an interface. He just plugged it in, loaded his brain with the information, carried it to its destination, and then they downloaded it. Okay, let's see. 46, right? Yeah, that's where we are. The statement that the lowest energy configuration of an atom is the one having the maximum number of unpaired electrons allowed by the Pauli principle in a particular set of degenerate orbitals is known as Hund's rule. That's the one where you can't pair them up. Like we have a p orbital. Right? You got to go like that, like that, like that before you can start pairing them up. So if you have 3 electrons, they go like that. If you have 4, then you can start pairing. That's Hund's rule. They're using a term there that we didn't talk about. Degenerate. In chemistry and physics, degenerate doesn't mean perverted. Degenerate means they all have the same energy. These orbitals are degenerate because they have exactly the same energy, amount of energy at that level. Okay. If you had an orbital here and one here and one here, those would not be degenerate. They're at different energy levels. But these are at the same, they're degenerate. I don't know where that name came from, but that's what it means. 47. Okay, we've got about 8 minutes. An element has an electron configuration of a core of krypton plus 5s, 4d, and 5p. 5s, 4p, 5,
4D10.
oh, 4d, excuse me. 4d10 and 5p2. Okay. Start from krypton and then move along. 5s2 would give you rubidium, strontium. And then you go across the transition elements all the way to cadmium, we cover these. And then you say, all right, we need two more. Indium, 10. This is 10. And krypton has 36 here, so 36 plus 10 is 46, 47, 48, 49, 50. That's correct. So where is that located in the periodic table? Right, 10 is here, it's a metal. It's to the left of that zigzag line. Okay. That's why the answer is C. About 48. Right, if we're going to find out what position they're in, actually, the next one is xenon core. And then 6s2, 6s2, 4f14, and 5d7. Okay. So if we're 5d7, that simply means that you're in the transition metals. You're filling the d orbitals. So it has to be a transition metal. I mean, we could go find out which one it is, but to answer the question, it's a transition element because you're filling d orbitals. And d orbitals are only filled in here. Okay.
Couldn't you, if you're given, like the X speed, you're trying to figure out what element you use,
Uh-huh.
couldn't you use the top and add all the others?
Yeah. Yeah, start from xenon, which would be 54. Right, there's 54. Then you drop down to the next one. Cesium, barium. It's these. Lanthanum, through the entire series of lanthanides, is 14, right? There's 7 orbitals, 2 electrons each. So we do 14 across here. Then we go back up to where lanthanum left off, hafnium. And we go 7 across from there. 1, 2, 3, 4, 5, 6, 7. This is platinum, which should have 78. Let's see if that's right. 54, 56, 56, 63, 77. Oops, 77. Is that right? No, it wouldn't be platinum then. It'd be iridium. Because it's 77, 21, 23, and 54, 77. It's iridium. Oh, I know why that is. Because lanthanum is not filling an f orbital. You go to cerium, that's where you start filling f orbitals. You go 14 across. So lanthanum has one of these, and then 6 more. 1, 2, 3, 4, 5, 6. That makes it iridium. How are we doing? Oh, right. Is it what time? Oh, 45. Okay, so we got a couple more minutes. Then we can find a convenient break point. Yeah, that looks like it. 49. All alkaline earths have the following number of valence electrons. All you have to do is count from the left. Right? How many valence electrons? Alkaline earths are the second column over, right? Okay, so it has 2 valence electrons. They're both s electrons. 50. Titanium has how many electrons in its d orbitals? Titanium. Well, find out where titanium is. Right, it's over there. Start with potassium and move over 4. Titanium has 22 here. And it's 2. You have scandium here, and then titanium. So this would be the D1, this would be the D2. It has 2 d electrons. Okay. Let's see, is that a good break point? Let's do 52. Because it's similar to the one we just did. Iron has so many electrons are unpaired in its d orbitals. All right. So if we're looking at iron, 26, right? Iron is in the 4th period, right? So it has 3 Ds. It's filling 3D. And if you count over, scandium, titanium, vanadium, chromium, manganese, iron, that's 6 d electrons. Now, what we're asking is how many of these are unpaired? Are you okay?
Okay, I see.
Okay. Yeah, 6 from the left means 6 electrons in the Ds.
Because the first one's 0, right?
No.
0, 1, 2, 3.
Oh, I see what you mean. Well, D. Yeah, if we have 3, if N equals 3, then L equals 0, 1, and 2. This is S, P, D. So D is 2. Right? So how many sublevels does it have? -2, -1, 0, +1, and +2. So it has 5 levels. Okay? And you got 6 electrons to put in those levels. So we use Hund's rule. 1, 2, 3, 4, 5, 6. So it's 1, 2, 3, 4 unpaired electrons for iron. All I see is puzzled looks and no heads are spinning, so that's good news. Now, when we get over to, let's see. I'm not going to introduce. I was thinking about throwing you a curve, and I said, no, that probably wouldn't be a good idea.
Probably not.
That'll ruin your weekend, right?
My brain might explode if you do.
So that's where we'll stop. We'll pick it up with 53.